morning, everyone, and welcome also on my behalf. So I will go and really the top level of how Gaia is operating and start going with that one before we really go into the data release 1 and all the details, what the reasons why you are here. This is the picture. You will hear from Andre Moitinho more about the visualization. This is coming from that one. I just want to make one note of it, of its beauty. In ESA site, where we are looking how interested the general community is to Gaia, this picture is at the same level of interest as the Rosetta pictures, which is quite surprising. We didn't expect that. I mean, Rosetta is something much more concrete in a way than Gaia, but apparently, in a wider public even, there is as much interest to Gaia as there is for Rosetta. And I think one of the things why people like this picture is that you see all the instrumental effects on it. It makes it more real, funnily enough. If it would be a beautiful image without any instrumental effects, maybe the effects wouldn't be that high. And what of course we have in this picture, when you zoom in and when you look at the visualization tools, you can see all kind of objects in Gaia data. So here we have the Magellanic Clouds, but we have also globular clusters. And these are not images, of course, these are star counts. So this means we are seeing the individual stars in these objects. We have the Carina dwarf galaxy in here. The same thing. It's the individual stars what we are seeing in these objects. It's not the image or the integrated light. No, it's the star counts. We see the stars in these galaxies. And the Gaia release contains information of those. And of course, when we made all this data available for the community, there were people very quick in analyzing data and utilizing it for science. And the first analysis was 9 hours after the release of looking the T-gas stars in the Magellanic Cloud, looking at the proper motions, taking out the systematic Magellanic Cloud proper motion, which is at the left lower corner here in this figure, looking at that one, taking out, and you see the rotation of the Large Magellanic Cloud. It was something that was done already with the Space Telescope, so it was a confirmation that is consistent, that the results are the same. But it's a good example of how people worked very quickly on the data and got scientific results out of it. Okay, let me move into the operations part. We are in routine operations since July 2014. And just a reminder that what Gaia is doing, we are scanning. And we are scanning, and then we combine the 3 motions. The satellite is spinning, the spin axis is precessing, and then we are in L2 going around the sun once every year. So it's three movements which together make the homogeneous coverage of the sky within the constraint that for thermal reasons we always have to keep the 45-degree angle to the sun so that we keep everything as stable as possible. The advantage of scanning is that we are observing all the time, 24 hours. We are all the time collecting real data. Of course, there are dead time. I mean, this was already anticipated before the mission. So we have to do orbit maintenance, typically once a month, but sometimes we can skip one because the orbit is good enough. We don't have to correct for it. We do have micrometeorites, so we get sometimes small hits, which we correct very quickly. This will be also taken care in the data processing. There will be more information on that in the astrometry part. But sometimes we have a big hit, but not very often, once a month, that we really lose even the spin a little bit. It takes some half an hour to recover. So sometimes we have gaps in our observing stream, but it is part as expected. We also have a contamination of water still in Gaia, and we have to decontaminate. Essentially, we heat and get rid of the water what has been collected to the optical surfaces. The last one we did in August, and after that, Gaia is for some time thermally unstable. We are now back in a stable conditions again. Every time we have come back with the transmission loss, it's coming later in and with a slower rate. So we are now hoping that we can peacefully observe. I'm guessworking here, but let's hope that the next decontamination is not earlier than 18. It's a guess. And of course, we have sometimes in the stations, we have weather problems, so we lose some bits of data. It can be storm in one of the ground stations, and then There is no memory on Gaia what data was sent down. So when it's sent down whether it's received or not. Now the nominal 5-year mission, so we are approaching the halfway of the nominal mission, is ending mid-19. What is the real end of Gaia? The real end is that we run out of consumable, which is the cold gas. And the cold gas is the one which is keeping the spin. So if we don't have cold gas, we cannot keep the spin. So if you don't keep the spin, your images are blurred. Astrometry from blurred images is not a good idea. So we estimate currently that that end is end of 2023, plus minus 1 year, because there is some extrapolation issues that the space weather makes the torque vary over time, which we are not able to estimate properly yet. Missions which live longer than the nominal time, that's not an unusual thing. So ESA has a standard procedure how missions are extended, and we are in this game already now. Obviously, we want to use Gaia as long as it works, and it's just part of the routine process of how to get the funding sorted out for the extended period. So we are going in Gaia, who are operating it and processing the data. In our mindset, we are going till 23. Where we are in the astrometry. Yesterday I looked, so we have 556 billion astrometric measurements. What we are observing on board, we are observing till 20.7, that's the magnitude limit. There is an onboard magnitude estimate error of the order of 0.3 magnitudes. So if you see on the Gaia catalog an object which is of 21st magnitude, it's correct. If you're missing an object of 20.5, it's also correct, because there is an estimation error on board. At 20.7, our detection probability is of the order of 80. So if we then on average see every star 80 times, we should get 80% of those 70 observations on average at 20.7. So the numbers to keep in mind. In crowded regions, we have an issue with the onboard resources. This is also something we knew in advance. If we look like the core, if you look at data release 1 and you look at the core of Omega Cen, you will notice that the fainter stars in that core are about 15th magnitude. Now part of that one is still that it's a tricky thing to do the core, but part of it is already happening on board, that we have too many stars to record at any given moment. So the magnitude limit in these extreme conditions are brighter. So what we do as a remedy in order to recover some of this, we have an imaging capability on Gaia. We cannot do it too often because the data would overwhelm us. We can do it occasionally, and Omega Cen is an example where we do it. So when we are passing Omega Cen, we get it to 15th or 16th magnitude observations as normal Gaia operations, but then we make these images which are sensitive to about 21st magnitude every time. Not with the full astrometric capability, it's an image with one row of CCDs only. So we have the data, we know the scene at least, even in the crowded regions.
Sorry, is that just a number of stars, or is it the density? So many paraseconds, so is there a critical density, or is it just, you have a lot in that field?
It's related to the fact that there is a certain time we have available to read one row. And in order to record the full row, we have to do already two things in the reading. We have to read slowly when we have a star and flash quickly on the dark patches of the sky. And in order to have the row read before the next row is coming in, we cannot have too many slow bits. And that limits the number of stars we can have in any single row. And then so it becomes a density issue then. Okay, the faint limit is 20.7. The bright limit is about 2 to 3 magnitudes. Anything what is fainter than 3rd magnitude is essentially always observed with Gaia. However, from about 3 to 6 magnitude, the sources are saturated. In principle, theoretically, it's not a problem, but let's see later in practice. From brighter than 2 second magnitude, we essentially never recover that with Gaia. And this is because the saturated smudge on the CCD is so big that Gaia doesn't see it as a point source, it sees it as an extended source. There is not enough memory and time to recover it. And then, of course, between 2 and 3, sometimes we get it, sometimes we don't get it. So it's the in-between region. So what we are also doing all the time with Gaia is that anything brighter than 3rd magnitude, we observe actually similar way as we do omega N, but this time the images are really tiny. They are just recovering the star itself. And we are looking into possibilities to do this a little bit more refined.
No, I should know this, but at what level of the windows passed on to XP and RBS? What's the cutoff level? Because obviously the special modes don't pass windows beyond the I'm presuming they don't get passed beyond the astrometric focal plane, is that right?
You mean the small images?
Well, no, just so
The bright star VOs, Timo. I don't think they're passed beyond AF at the moment.
No.
So what is the effective cutoff then for XP and RBS? I should know the RBS, but I forgot.
So in a way, what happens at, what is the difference, it's actually on my next slide, but
Okay, sorry.
if I don't remember to say it, come back. Okay, going to photometry. So the number of photometric measurements is at the moment 120 billion. It is exactly the same magnitude limit because how it works on Gaia, when Gaia says that this is bright enough star to observe, we get astrometry and we get photometry. They are coupled to each other. We don't get one or other, we get both. The spectrophotometry, which is done with, you see here in the graph with the blue part and the red part, they cover from, combined from 330 to 150 nanometers. Of course, one has to recall that when we do astrometry, which is most of the green CCDs on this picture, it's also good for photometry. It just doesn't have any color information. But that is the information which is extremely useful for variability, because there you have the millimagnitude accuracies very quickly. So the photometry is kind of two-part. There is the broadband from astrometry, and then there is the spectrophotometry with BP and RP. Again, in crowded regions, exactly the same thing, because it's the same decision-making where we say we observe, we do astrometry, and we do photometry. So we do it, and if we run out of resources in crowded regions, we run out of resources. Now, these special images, what we do for the very brightest stars, it is only done in the astrometric field. So there will be no photometric data for the brighter stars unless Gaia itself detects it. So essentially, anything brighter than 2nd magnitude, we don't get. Anything between 2 and 3, we get sometimes. Anything fainter than 3, we get always. And again, we are looking into possibilities to expand this one, because even if it's badly saturated, it wouldn't be a bad idea to have a BP-RP spectrum of Vega. Even if maybe it cannot be used to anything, but at least we have it. So we look to possibilities here. Spectroscopy. We have 11 billion spectroscopic measurements. Note that the accuracy on these counts is in 500 millions. So I think there are many spectroscopic surveys who would be happy with 500 million spectra, but that's the accuracy we count. The limiting magnitude here is different. So here is really a different decision making. There is an extra decision making. Is the object brighter than 16.2 magnitude? So if it's fainter, we will never do it. Again, there is an error in the magnitude estimate, so the border is not as sharp as one would expect. One thing to remember, the instrument is called radial velocity spectrometer. It means that it's the radial velocities which is the main product of this instrument. So we get the sample of more than 100 million stars. It's for radial velocities. It looks, if you have the end of mission spectra at the faint end, if you're not a spectroscopic, well, maybe even more, if you are spectroscopist, it looks like noise. It doesn't look like a spectrum. You have to go to something like 12, 13 magnitude before it looks like a spectrum. You could think it in two ways, that we have two surveys with spectroscopy. It's the same instrument, it's the same wavelength coverage of the calcium triplet with a resolution of about 10,000. For the bright stars, it really looks like spectra. It's a spectroscopic survey. When you go fainter and fainter, it starts to look more and more noise. You still can get the radial velocities with a certain accuracy out of it. Again, in crowded regions, there is a problem. Less so because we don't even try to get anything fainter than 16th magnitude. But still, because it is kind of objective prism idea, the spectra at certain points start to overlap. So the crowding is a problem in crowded regions. Again, the same selection at the bright end. We have no spectra for brighter than the 2 to 3 magnitude because that's selected upfront on board. And when we are looking for this more complex data collection, we might, it's a technical open issue yet, we might also get it for the brighter stars, but it's not really our goal to do that. So not looking to the data release 1, but looking for the whole mission, the nominal 5-year mission, what are the estimates of the end of mission performances? So anything at the bright end, so I'm talking about here from 6 to 12 magnitude, like spectroscopy, the radial velocities, it's systematics defined. So we will get as good as the systematics. The same is for the PP and RP photometry, even to 15th magnitude. It's all about accuracies, and I think there will be sessions with the photometry, so we will hear more about the precisions and accuracies of what are achievable. When we go to spectroscopy and radial velocities at the 15th magnitude, we are talking about 13 kilometers per second. When we are going to the really faint end photometry, then the integrated photometry, we are talking about 60 to 80 millimagnitudes. For astrometry, we are talking about half a milliarc second parallax errors. When we go to brighter stars with astrometry, when we go to 15th magnitude, then we are assuming 25 microarc second parallax accuracy. There is quite a lot of confidence that this is reachable. It looks good. We are working towards the 10 microarc second domain for the very brightest stars. Obviously, this is fully dominated by systematics. So it's all about do we get the systematics under control. So at the moment, we are not yet there. We are looking for other effects, calibration effects, which are at the higher level. The only thing we can say that at least we don't see anything which is totally killing the possibility. So we have to just process towards that goal. Okay, there will be many presentations now focusing on the data release 1. So I spent a few minutes on showing something what Gaia is doing, has been doing, is not yet visible, but will be there in the end. So one of the things what we said we are going to do are asteroids, and we have been making this statement. So it was nice to check, do we actually detect the asteroids? So there was a quick check made of known asteroids, 50,000. And we detected them, and they are there where they should be, at the ecliptic plane. And here the contribution of Gaia it's manifold. 250,000 main belt asteroids, which will get much better orbits. So we have much better classification of different orbital families. They are all done with the same photometric system. I think this is probably not yet fully appreciated, that we have a 4-pi coverage in a single photometric system without the trouble of atmosphere. And asteroids will be all done in the same system, all the stars as well. Other topic, there will be no spectroscopic discussion further here, but we have the 11 billion spectra, and for the bright stars, there is an element of double-lined spectroscopic binaries. So spectra is good enough. We have multi-epoch observations, so we will be very good in seeing bright stars which have variability in the spectral ranges. The more general variability thing will be covered on the Friday session. And yet another example, color magnitude diagram. So the first data release does not contain the Gaia colors, But with the preliminary photometry, we have it. And if you look at the omega sen column magnitude diagram, it looks like astrophysically making sense. So the data is there, it is collected, it just needs to be calibrated and processed. Let me just then show one example of what it was a cute example and quite exciting in a way to us that where the Gaia is working properly. We released in advance one position from the data release 1 in summertime. It was because there was a star being occulted by Pluto. And there was an estimate before Gaia data was used. And if you look the red line, so the many European observatories were very keen on looking at this one because they would see the occultation perfectly. And we said, well, let's release the Gaia position for this star and see what happens. And what was done, it moved, unfortunately for Europeans, out of Europe to closer to Africa. Still, you could observe it from Europe. And the nice relief to us, which gave confidence that we are on the right track, is that when they observed it and then looked the data and looked where is the central point, this is what was the reality. This is where it was. So this is what Gaia predicted, this is where it was. And this is where it was thought to be. It gives a confidence that we are on the right track and getting good results. Let me conclude. Gaia is working, it's collecting data. It is on its way to fulfill the promise. Of course, there is a lot of data. It needs a lot of processing. And the processing task is huge. If you have a billion stars, we don't probably have million issues, but we do have thousands of issues to solve with the billion stars. And this is what the Data Processing Consortium is doing, and I think we are very thankful for that exercise and that is happening. And I also hope that the community realizes the work and the effort what is going on that one and gives the full support to these people who are doing the data processing. And I stop here and I'm open for questions.
Okay, thanks, Timo. I think we have time for a couple of questions. I'm sure there are plenty.
You said that the orbit is relatively stable and there aren't many updates needed, and I had heard that there was some ground-based observing done to support the mission. Is that a secondary application now, or are the ground-based observations still important to the analysis?
It is important to do the ground-based, and the program is ongoing. It is also one of the DPAC activities, and we do it every day. And it is needed to determine the Gaia orbit. Because if you are looking for example, asteroids, the parallax, whether you observe from Gaia or Earth, is big enough to move the position. So if you do the orbital calculation, you have to know precisely where Gaia is. And these observations are needed, they are done, because we need to know the velocity to 2.5 millimeters per second. We need to know the position to 150 meters. And for this, we need the special measures.
Will Gaia also provide a spectral type classification to the stars?
Yes. So one of the elements in the data processing of Gaia was that there is a big European consortium who is processing the data. And one of the things like spectral classification, it is obvious that when you have photometry, spectroscopy, and you have the astrometry, you can do very good classification. And it's best to do done for the whole sample, and it will be done. It is one of the later products. Because if we would just put the raw data out, of course the community would do it, but there would be 20 different ways to do it, and nobody would do them all. Everyone would do a topic of their own. So it was considered at the European level that the best way to tackle this one is to let this task also to the consortium. And there is an important element of it. It is also our validation and check. It has to make sense what we get out. So it's for us also important internally.
It looked like those RES spectra were good enough to do some abundance analysis on. And so that would be a good motivation for getting the spectrum of Arcturus, which is a very bright star. It's a really useful standard, so I implore you to do that. But regarding my previous question, I'd like to know do you know what the actual space density is where this limit occurs? You know, 1 star per 10 arc seconds, 1 per arc second. I don't know, because I'm interested in the bulge, and so it would be useful for me to know. Oh, okay. Well, I'm not going to be able to see everything at this point. You know, at this latitude, for example.
So you're going back to the crowding issue. So it really is, if one really goes to the fundamental element what determines, it is really in a one row of CCD level. So so what Gaia is doing when it's observing and saying, I see many stars, too many to observe, it ranks them with magnitude and says that I can do maximum like 8 on a single row of width of 1 CCD, and I allocate those windows to these 8 stars, and anything else I have to skip.
But there should be like a density.
It's a few 100,000 stars per square degree for the astrometry, where the crowding sets in. And for RVS, I think it's of the order of 35,000 stars per square degree. And once you're above that, the crowding sets in. It's not that you will get a gradual decreasing of the completeness, and on average sources will have less observations. But in principle, everything should still be, almost everything should still be observed.
Yeah, the problem with the per square degree density determination is that the decision is not made in that scale. The decision making is in a much smaller scale. But the numbers, what Anthony was saying, is the sort of ballpark field.
Red giants in the bulge, and every 10 arc seconds, there's another red giant in there. So,
Yeah.
So I just wanted to have a mental picture of, well, this is too dense.
Okay, maybe we can discuss offline. Mario, you want to?
Can you say a little bit more about the asteroid data? When is it going to be released, and what are you going to be releasing? Are you going to be computing orbits, or are these going to be just astrometry measurements?
The orbits are going to be later. There is a plan already for the next release to contain some orbit calculations and some asteroids, but this is at the testing phase. So it's in a way in the, so how do you say it? We have a plan what we try to get for the next data release. We know which are definitely not going to be in, but asteroids are in for the next one. Whether they will make it, we have to see the quality, what is coming from the processing.